Okay. Today we are going to talk about quadratic functions. This is section 3.2. So, just to start us off, quadratic functions are second degree polynomials. These commonly arise in problems involving area and projectile motion. As usual, let's jump right into an example that we can work on. So we have that a backyard farmer wants to enclose a rectangular space for a new garden. She has purchased 50 feet of wire fencing to enclose 3 sides and will put the 4th side against the backyard fence. Find a formula for the area enclosed by the fence if the sides of the fencing perpendicular to the existing fence have length L. Okay, so in this case it would be good to draw a picture. So here I actually have a picture for us to picture what's going on in this problem. I have this garden that's enclosed on 3 sides by this wire fencing and on the 4th side by the backyard fence. So the wire fencing is only covering 3 sides here, right? I have 80 feet of wire fencing, and I want to find the area enclosed by the fence if the sides of the fencing, or I want to find a formula for this area if the sides of the fencing perpendicular to the existing fence have length L. So if those have length L, we're going to call the other side length W for width. So if we have 80 feet of fence available, then I know that L plus W plus L is equal to 80, right? Because this side is also L over here. In other words, 2L plus W equals 80. Now, I also know that the, well, I suppose I can finish up on this one. This lets me write this variable W in terms of the stuff that I was given. I was given these L's, right? So I really want for this formula to be in terms of just L. So I can solve for W to get that W is 80 minus 2L. And now whenever I come up with a formula for the area of this rectangle, this is going to be L times W, which is L times, well, W is 80 minus 2L. So I could say that A of L is 80L minus 2L squared. So here, the formula, this formula represents the area of the fence in terms of this variable, L. Moving on, let's talk about some properties of quadratics. Okay, and the point of this was this is a quadratic function, right? And we're going to come back to this later. So, anyway. Quadratics have this short-run behavior called a vertex. They have this feature called a vertex where they change direction. The vertex of the quadratic tells us about the transformations of that quadratic. It tells me how much it's been shifted vertically and horizontally. The typical vertex of a quadratic, so the vertex of f of x equals x squared, is at the origin. It's at 0, 0. That's why the vertex informs me as to what transformations have occurred. Because if my vertex is moved, then my quadratic has moved by that amount. So let's look at an example. Let's write an equation for the quadratic graphed below as a transformation of f of x equals x squared. Then we'll expand the formula and simplify the terms to write the equation in standard polynomial form. Remember, standard polynomial form has the highest power first, and then each subsequent lowest power after that. So I can tell from this graph that this is a quadratic that has been shifted. Let's see. My vertex is right here, right? So my vertex has been shifted to the left 2 and down 3. Because this has been shifted to the left 2 and down 3, right? This is like a times, right? There might be some stretch factor here. That's why I'm putting an a. This is like a times f of x plus 2 minus 3. So this is like a times x plus 2 quantity squared minus 3. Now if I want to find what kind of stretch or shrink has occurred here, I need to find another point on this quadratic that is not this vertex and plug the information of that point in. Notice here I have the point 0, negative 1. So if, say, y is equal to this, then negative 1 is equal to a times 0 plus 2 squared minus 3. So negative 1 is equal to 4a minus 3. I add 3 to both sides. I get 2 equals 4a. So I get a equals 1/2. So I could say that this function is represented by the formula, we'll call it g of x if our original function was f of x, is equal to 1/2 times x plus 2 quantity squared minus 3. If I want to write this in standard polynomial form, I have to expand this term. Remember that whenever I square something, I'm just multiplying it by itself. This multiplies out like this using the distributive property of multiplication. And now this is, let's see, x squared plus 2x plus 2x plus 4 minus 3. This is 1/2 times x squared plus 4x plus 4 minus 3, which is 1/2 x squared plus 2x plus 2 minus 3, which is 1/2 x squared plus 2x minus 1. This is the equation of this quadratic in standard polynomial form. Speaking of standard polynomial form, I have a few forms of a quadratic. I have standard form, where I'm given this quadratic as f of x equals a times x squared plus b times x plus c. Obviously here, a can be anything that's not 0. So a can't be 0, right? If a is 0, this is not a quadratic anymore. Similarly, I can write this in what is called transformation form or vertex form, which is a times x minus h quantity squared plus k. Again, a can't be 0 here, or else this is not a quadratic. So from this vertex form, I can actually find the vertex of the quadratic, because the vertex is at the point hk. So if I have the quadratic, f of x equals 3 times x minus 5 quantity squared plus 7, that has a vertex at 5, 7. Notice that on the inside here, the default operation is subtraction. So if I'm subtracting a number inside here, then that x value is actually positive. 8 times x plus 1 quantity squared plus 2 has a vertex at the point negative 1, 2. This is a shift left 1, and up 2. The quadratic 7 times x plus 9 quantity squared has a vertex at the point -9, 0. This is a shift to the left 9 units and up or down 0 units because I'm not adding or subtracting anything at the end here. If I have a quadratic in standard form, my vertex, hk, is located where h, so remember standard form we wrote earlier, just a second ago. Standard form is a times x squared plus b times x plus c. So h, that's the x coordinate of my vertex, is -b divided by 2a. And k is just the corresponding y value. It's what I get if I plug h in to the function. So let's look at some examples where we have to do this. Find the vertex of this given quadratic. Write the quadratic into transformation form or vertex form. What I sometimes find to make these problems easier is if I go ahead and I write what a, b, and c are. So a is the coefficient of that quadratic term, which is 2. B is the coefficient of the linear part, which is -6. Notice how I have to take the sign with the number. And C is 7. This means that H is -b divided by 2 times A, which is -6 divided by 2 times 2. This is 6 divided by 4, which simplifies to 3/2. Now, K is f of 3/2. It's just what I get if I plug h into this function. So I'm plugging h into this function here, right? So this is 2 times 3/2 squared minus 6 times 3/2 plus 7. This is 2 times 9/4 minus 9 plus 7, which is 9/2 minus 9 plus 7. This is -9/2 plus 7. And 7 is 14/2, so this is positive 5/2. Let me move this problem down a bit more here. So I got that K is 5/2. I had H was 3/2. So my vertex is at the point 3/2, 5/2. So my vertex form is f of x equals a times x minus h quantity squared plus k. Earlier I said a was 2, so f of x is equal to 2 times x minus 3/2 quantity squared plus 5/2. All right, let's look at one more here. Write this equation in standard form and then in transformation or vertex form. So to write this in standard form, notice that I don't have my highest power first and then my second highest power second and so on. So this is just asking for me to rearrange it first before I put this in vertex form. So I just rearrange this to be g of x is equal to x squared minus 6x plus 13. Now this is in standard form. Now to write this in vertex form, I need to find a, b, and c. A is the coefficient of my x squared term is 1. If you don't see a number there, the coefficient is 1. Coefficient of B, yeah, the coefficient of B happens to be -6 again, just by coincidence. And C is 13. So H is opposite of B over 2A. This is -6 over 2 times 1. This is +6 over 2, which is 3. K is f of 3, or g of 3, rather, which is 3 squared minus 6 times 3 plus 13. This is 9 minus 18 plus 13, which is 4. So my vertex is at the point 3, 4. My vertex form is going to be 1, which we actually don't have to write, but maybe we'll erase it in a minute, right? That's A times x minus h, so x minus 3, quantity squared, plus 4. This is my vertex form. And again, we don't need to write that 1. I can actually erase that 1. Let's look at this process called completing the square. We're only going to do one example of this, but it's maybe good to look at one example so we have seen it if we need to use it later. This is another way of rewriting a formula in vertex form. Usually doing it the other way is faster, but this can sometimes be useful for certain types of problems. So the best way to learn completing the square is by doing it. So we're going to start by factoring the leading coefficient from the quadratic and linear terms. So I'm going to factor 2 from both this quadratic term and this linear term. So this first term and this second term. I'm going to factor a 2 from them, which gives me 2 times x squared minus 6x. And at the end here, I still have plus 14. Next, I need to add something into these parentheses so that this quadratic becomes a perfect square. In other words, I'm going to make a side note in green, and I'll come back to blue once the side note is over. In other words, I'm looking for values P and Q such that, oh, I did not mean to switch to the highlighter, such that x squared minus 6x plus P is equal to x minus Q squared. X minus Q quantity squared. There we go. So here, notice that, how should I phrase this? Q, this term here needs to be half of this middle term. Because if I were to multiply this out, so if I were to multiply the right hand side out, this left hand side would stay the same. Multiplying this right hand side out would give me x squared minus 2qx plus q squared. So this means that negative 6x needs to be equal to negative qx, and also p equals q squared. Here, we should see that if I divide both sides and eliminate everything I can, I should get that q is 3. So I want for x squared minus 6x plus p to be equal to x minus 3 quantity squared. Well, if this is 3, then this p, if q is 3, then this p is 9. So I want to have this on the inside of my parentheses. So I'm going to rewrite the stuff that I had. I'm going back to the problem in blue. I had 2 times x squared minus 6x. I'm going to leave some room here. And what did I have? Plus 14? Yes. So I need to add a 9 inside of these parentheses. But I don't just get to add a 9 inside of these parentheses for free, because I've now actually changed this expression, right? In order to keep this balanced, what I have to do is I have to subtract the number that I've added to this equation. But notice that I didn't just add 9 to this equation, I added 2 times 9. Because if I were to distribute this 2, right, this 2 would get multiplied to the 9, and 2 times 9 is 18. So to keep this equation exactly the same, I need to subtract 18 at the end, or to keep this formula exactly the same, rather. Now if I simplify, I said that x squared minus 6x plus 9 is going to factor to be x minus 3 quantity squared. And now 14 minus 8 is minus 4. And now this is written in vertex form. We may look at more examples of this later. Let's return to our problem involving that backyard garden from the beginning of the section. We came up with the formula A of L is 80L minus 2L squared. So what I want to find here, so this is saying, what dimensions should she make her garden to maximize the enclosed area? So notice that if we were to graph this, this would be a vertically reflected quadratic function. So it would look like this. It would look like a frown if we were to graph this. Notice that this has a peak, right? This function has a peak. This peak we call a maximum. So I want to find this maximum, and I want to find what dimensions of the garden maximize this enclosed area. So in order to do that, I have to find the vertex, right? Of course, this maximum is going to occur at the vertex of this quadratic. So to find the vertex of this quadratic, let's see. Maybe I should write this in standard form. In standard form, this would be A of L is equal to negative 2L squared plus 80L. I just rewrote it like this because it makes it easier for me to see what A, B, and C are. Here, A is negative 2, B is 80, and C is 0. I don't have that constant term, right? So this means that H, the horizontal component of my vertex, is 80, or negative 80, rather, divided by 2 times negative 2. This is negative 80 divided by negative 4. And this is 20. If I want to find k, I would just plug h into my function. K is negative 2 times 20 squared plus 80 times 20. This is negative 2 times 400 plus 80 times 20 is 1600. This is negative 800 plus 1600, which is 800. So the maximum value of this function is 800 square feet. This occurs when L is equal to 20 feet. Now I want to find the dimensions of this, which means I want to find W as well. Remember we said 2L plus W is equal to 80 because this is the amount of fencing that I had. So 2 times 20 plus W equals 80, or W plus 40 equals 80. This means W equals 40. So the dimensions of the fence that maximize the area contained by the fencing are L equals 20 and W equals 40. Let's look at another example. This is about revenue. A local newspaper currently has 84,000 subscribers at a quarterly charge of $30. Market research has suggested that if they raise the price to $32, they would lose 5,000 subscribers. Assuming that the subscriptions are linearly related to the price, what price should the newspaper charge for a quarterly subscription to maximize their revenue? First, I need to come up with a formula for revenue. Revenue is just the amount of money that a company brings in. So revenue here is, here, let's say that we have C, which is charge for per subscription. And we have S, which is the number of subscribers. Then revenue is just C times S. Now, the number of subscribers changes to the price, so we need to find a relationship between those variables. I know that S is 84,000 and C is 30, and that if they raise the price C to 32, then they would lose 5,000 subscribers. So S would be 79,000. So I can find a linear equation relating these two quantities. I can find the slope of this, which is 79,000 minus 84,000 divided by 32 minus 30, which is negative 5,000 over 2, which is negative 2,500 subscribers. And next I can set this up as S equals negative 2,500 times C plus B. Well, when I have 84,000 subscribers, I have 84,000 subscribers whenever I charge $30 for the subscription. If I multiply out and I solve for B here, I'll get that B is 159,000. This gives us the linear equation. S equals negative 2,500 C plus 159,000. Remember earlier that we said revenue is C times S. Well, in this case, that means that revenue is C times negative 2,500 C plus 159,000. Whenever I multiply out, I get negative 2,500 C squared plus 159,000 C. And now I have to find, I have this quadratic equation for revenue as a function of the subscription charge. So if I want to find the price that maximizes revenue, I want to find the vertex. I know that H is, here I have A is negative 2,500. B is 159,000. C is 0. So H is negative 159,000 divided by 2 times negative 2,500, which ends up being positive 31.8. So this is the cost or the charge that maximizes revenue. If I wanted to find what that maximum revenue is, I could plug this into my function. I could do negative 2,500 times 31.8 squared plus 159,000 times 31.8. This is $2,528,100. So I have a max revenue of that amount when the charge is $31.80. Let's look at intercepts. As with any function, I can find vertical intercepts of a quadratic by plugging 0 into the function. And I can find horizontal intercepts by solving for where the output would be 0. Notice that depending on the location of the graph, I might have 0, 1, or 2 horizontal intercepts. Let's look at some examples of finding these. If I want to find the vertical intercepts of this given quadratic, and by vertical intercepts, I mean vertical intercept, there's only going to be one vertical intercept. I just find f of 0. This is 3 times 0 squared plus 5 times 0 minus 2. This is going to be negative 2. So I could say that this has a vertical intercept at the point 0, negative 2. For horizontal intercepts, I have to set this function equal to 0 and find what x values cause this function to be 0. Whenever I can, the best way of doing this is by factoring this function. Thankfully, this function factors pretty easily. I need two numbers that multiply to get 3 times negative 2, which is negative 6, that add to get 5. The larger is positive because they add and get a positive number. So these are 6 and 1, right? These are 6 and 1. So I can now break up this quadratic as 3x squared plus 6x minus 1x minus 2 equals 0. I'm going to factor by grouping. I'm going to group my first two terms. I'm going to group my last two terms. I'm going to put a plus sign in between these and keep that minus sign with this x. Now out of each set of parentheses, I factor out the largest thing that I can. So I factor a 3x out of these first two terms to leave me with x plus 2. I'm going to factor out a negative 1, or just a minus sign, from this next set of parentheses, which leaves me with an x plus 2. Notice that these two sets of parentheses are 0, or not 0, but these are the same thing. Because these are the same, 3x times x plus 2 minus 1 times x plus 2 is the same thing as 3x minus 1 times x plus 2 equals 0. And I can now set each of these things equal to 0 individually. I get x equals 1/3, x equals negative 2. So my horizontal intercepts here are at the points 1/3, 0, and negative 2, 0. Let's see. And for another one here, this quadratic is not easily factorable. So what I can do instead of factoring this, because this is not going to be easily factorable, is I can try to rewrite this into vertex form. So let me write a is 2, b is 4, and c is negative 4. So h is opposite of b over 2a, which is negative 4 over 2 times 2. This is going to be negative 1. B, or not B, but K, is f of 1, which is 2 times 1 squared, plus 4 times 1 minus 4. This is, let's see, or rather these are negative ones, right? That makes actually a big difference. So this is negative 6. So this function can be written in vertex form as 2 times x plus 1 squared minus 6. And if I set this equal to 0, I can actually try to solve for x now. If I add 6 to both sides, I get 2 times x plus 1 squared equals 6. Divide both sides by 2, and I get x plus 1 quantity squared equals 3. I can now take the square root of both sides, and I get that x plus 1 is plus or minus the square root of 3. And I subtract 1 from both sides to get that x is negative 1 plus or minus the square root of 3. So I have 2 horizontal intercepts here. My horizontal intercepts are at the points negative 1 minus root 3, 0, and negative 1 plus root 3, 0. These are my horizontal intercepts for this quadratic. And the last topic is quadratic formula. For a quadratic function given in standard form, the quadratic formula gives the horizontal intercepts of the graph of this function. The quadratic formula is x equals negative b plus or minus square root p squared minus 4ac all over 2a. Now, we shouldn't immediately jump to the quadratic formula when I see a quadratic, because oftentimes if I can do something like factoring, it's going to be easier and way faster, and I'm going to be less likely to make a mistake. But if I can't factor, and I maybe can't even get something easily in like a vertex form, then this is a great tool to use to find those horizontal intercepts. So we can look at an example right here where we have to use this. A ball is thrown upwards from the top of a 40-foot tall building at a speed of 80 feet per second. The ball's height above the ground can be modeled by the equation h of t equals negative 16t squared plus 80t plus 40. What is the maximum height of the ball? When does the ball hit the ground? To find the maximum height of the ball, I have to find the vertex of this quadratic. So the vertex of this quadratic, well, first let's say A is negative 16, B is 80, and C is 40. We're going to need these for several reasons. Let's just keep these in mind. So the vertex, let's see, I have h equals negative 80 over 2 times negative 16. This is positive 80 over 32, which is 5 halves. K is h of 5 halves, which is negative 16 times 5 halves plus 80 times 5 halves plus 40, which is 140. So the ball reaches a maximum height of 140 feet after 2.5 seconds. To determine when the ball hits the ground, we have to find where the height is 0. And we could do this using the vertex form of this quadratic, or we can use the quadratic formula. So let's use the quadratic formula for this case. So we want to find where the ball hits the ground, which is going to be where my function is equal to 0. It's going to be where it has a horizontal intercept. So this is going to be t equals, because I have these variables t, right? So my quadratic formula is opposite of b plus or minus square root b squared minus 4ac all over 2a. And this is going to be negative 80 plus or minus square root 80 squared minus 4 times negative 16 times 40 all over 2 times negative 16. This is going to simplify to negative 80 plus or minus the square root of 8,960 all over negative 32. This square root doesn't simplify nicely, so we'll just use a calculator to approximate these values. If t is negative 80 minus square root of 8960 divided by negative 32, because remember I have this plus or minus, so I'm going to look at both cases individually. This will be about 5.458. If t is equal to negative 80 plus square root of 8960 all over negative 32, this is going to be about negative 0.458. And now t here represents time, and it doesn't make sense for us to have negative time, right? So as a result, the second answer doesn't make sense. So our answer here is going to be the first one that we got. The ball will hit the ground. after 5.458 seconds. Okay, and that will be all for 3.2. 3.3 will go up on Monday, and I hope that y'all have a great rest of your day.